our first lecture, we briefly discussed the concept of tabulating elements based on specific properties. We saw how this idea was employed by Aristotle in his attempt to explain the four putative elements of his day: air, earth, water, and fire, tabulating them by the properties hot and cold, as well as dry and wet. Then we saw how Mendeleev and his contemporaries in the early 1800s started to apply this presentation style using the elements as we know them today. We talked about how his game of cards and his amazing ability to predict yet undiscovered elements by identifying gaps in that game played out in his day. But now we have surpassed even the great Mendeleev in our understanding of atoms and the elements that they comprise. Our discussions on the structure of atoms has given us an understanding and perspective that allows us to take an even deeper look into the periodic table and understand just how beautifully and elegantly it is organized. The modern periodic table arranges elements spatially based on their atomic structures. In doing so, it creates a graphical tool that arranges the elements in a way that helps us to predict and understand their properties. Properties like the phase of pure elements at normal temperatures and pressures. Notice how rare liquid elements are, and that the gases and the solids are all clustered together in different regions. Boiling points and melting points also create very interesting patterns. We can see that metals have their own region of the table, while nonmetals cluster elsewhere, both of which are separated by a smaller group of elements that we call metalloids, and these have properties somewhere in between the two. Radioactive elements tend to be found in a specific region of the table as well, and the list goes on and on. Most of these properties involve complex topics that we aren't ready to tackle just yet. But we are ready to explore a few of the most fundamental trends in elemental properties revealed to us by the periodic table. But before we can accomplish even this, we have to take a look back. Let's bring the knowledge that we have gained in the past two lectures to bear on Mendeleev's game of cards and on the periodic table itself. The periodic table, as we are most accustomed to seeing it, looks something like this. A grid of elements and symbols with a curious valley running through the middle. And we'll get to that valley in a moment. But first, let's consider the most obvious organizational feature of the table. Elements get more and more massive as we read across the table from left to right, just the way that Mendeleev had organized them originally. But the modern table doesn't use atomic mass of each element the way Mendeleev did. The true factor driving the periodic properties is actually the atomic number, the number of protons in an element's nucleus. It was just a fortunate coincidence for Mendeleev that, with very, very few exceptions, as the number of protons in an atom increases, so do the total number of nucleons, including neutrons. This means that atomic mass and atomic number follow roughly the same trend. We now know, courtesy of Ernest Rutherford and his contemporaries, that it's the number of protons that dictates the identity of an element, not necessarily its atomic mass, as Mendeleev had thought. The second order of organization is the columns of the table. Recall that Mendeleev had chosen his columns in such a way that each contained compounds with similar types of properties. Lithium, sodium, and potassium are all metals that react similarly to one another and are found in similar combinations with other elements in nature. And here they are. They reside in column 1. Neon, argon, krypton, all unreactive gases, and they all reside here in a separate column, all their own as well. But what Mendeleev didn't know, indeed what he couldn't possibly have known in his day, was that the reason these elements reacted so similarly is that they share a similar valence shell electron configuration. Notice that lithium's valence shell has a 2s1 configuration. Sodium has a 3s1. Potassium, a 4s1. And on the other side are noble gases, neon with 2s2, 2p6, argon with 3s2, 3p6, and krypton, whose valence shell contains 4s2 and 4p6 electrons. So we have the benefit of understanding that it's the electron configuration of an element that gives it its own unique reactivity. and that similar valence electron configurations lead to similar chemistries. Which brings me to my next point about the table's organization. By arranging columns of similar elements, we automatically create rows within the table. More importantly, each row begins with the expansion of an element's electron cloud into a whole new principal energy level. This level of organization itself is a remarkable testament to Einstein's famous quote, "God does not play dice." Certainly, the most remarkable thing about the table is how such a simple method of categorizing the elements can explain some of the most complex properties of the most exotic elements that we know of. When we organize elements in this way, by increasing their atomic number with new rows beginning with the first electron to populate new principal energy levels, the resulting table is encoded with many, many trends in the properties of elements, some of which are very intuitive and some of which you might find surprising, but all of which help us to better understand the behavior of matter. The overriding theme that we're going to notice in this discussion is that trends in many properties of atoms are dictated primarily by just two important factors. Trends among elements in the same row are most often dictated by the charge on the nucleus, and trends among elements in the same column are very often dictated by the number of electron shells in the electron cloud. So let's take a look at a few of these periodic trends and the forces that drive them, shall we? Let's begin with a very simple property, the atomic radius. And let's take a look at how that changes as we move through columns of the periodic table. Specifically, let's take a look at a few elements from group 8, helium, neon, argon, and krypton. Now, each of these elements has an electron cloud with a progressively larger and larger set of shells. We know from the periodic table that helium has an electron configuration of 1s2, neon of 1s2, 2s2, 2p6, argon, of course, has a neon core with a 3s2, 3p6, and krypton has an argon core with a 4s2, 4p6 valence shell. Now, this is what's going to drive the trend in size. Valence shells are very large, and progressively adding more and more of them results in creating an atom which is larger and larger. Another way to think of it is like this. Helium has a 1s subshell, which makes its valence shell 1. A neon is building upon that, adding an entire second layer of electrons to the cloud. Argon is like a neon that has been expanded by an entire layer. And krypton is like an argon that is yet again expanded by a whole other layer, driving a trend in which the radius decreases as we move up a column. Of course, another way to say this would be that it increases as we move down. The driving force, again, within columns is valence shells. But there's even more to trends in the radii of atoms that the table will let us determine. Let's consider what happens as we move across a row of the periodic table instead. In this case, we'll do row 2. So we'll be looking at lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, and neon. Now in this case, we can't use valence shells to try to determine which is larger because they all have the same valence shell. Adding additional electrons to lithium, at least in this region of the table, increases the number of electrons in that outermost shell, but notice that in all cases, we have an electron configuration which indicates to us that the valence shell is the second shell. So this is no longer the driving force in the radius of these atoms. Instead, what drives their size is the positive charge on their nucleus. As we go from left to right across the table, it's true that elements become more massive. However, most of that mass is concentrated in their nucleus. And when we add extra protons, we get extra charge. So we're going from lithium, which has a nucleus containing only 3 protons here on the left, all the way to neon, which contains 10 protons at the right of the row. That means that the nucleus of neon pulls much, much harder on those electrons in the second shell, and therefore results in a squeezing down of that valence shell. So the very counterintuitive idea here that a more massive element could actually have a smaller radius is easily justified when we consider the effects of this nuclear charge. So our trend again, decreasing atomic radius as we go left to right across a row, is driven by the charge on the element's nucleus. So our general trends in atomic radius can be summarized as thinking of it this way. As we move from left to right across the table and bottom to top across the table, we decrease the radius of the atoms. This general trend holds well for S and P block elements, and it even works as a general rule for the D and F block elements. But a word of caution is in order because the complexity of the D and F subshells can sometimes cause slight deviations from those trends. Just as important as understanding trends in the atomic size is the understanding of trends in the size of ions. Now, just as with atomic size, let's focus on some of the S and P block elements because they're the most well-behaved and will help us to understand the overriding trends that we see. As an example, let's consider one column of the periodic table, group 1. As you can see, group 1 atoms tend to form +1 ions in order to achieve an octet of electrons. The size of each positively charged ion increases dramatically as we step down the periodic table. And the reason for this is easily explained. As we work our way down the column, we are adding additional energy levels to the ion's electron cloud. Biological systems, like the muscles in your body, use sodium and potassium ions differently, and they rely on differences in the size of those ions to shuttle them to the right locations within cells, ensuring that they play their very important but differing roles in critical functions like muscle contraction. Trends in ion size across rows are a little bit less regular because the quest for octets makes it more attractive for elements like those in groups 1, 2, and 3 to lose electrons to form ions. This means that they can lose a valence shell on ionization, making them much smaller. But those in groups 5 through 7 typically prefer to gain electrons to form an octet, retaining and actually expanding their valence shell. Group 4 elements rarely ionize, but when they do, they have to lose 4 valence electrons to form an ion. And of course, the noble gases themselves are excused from this discussion because they already have their octet. This means that they're essentially never found as ions in nature. Now, some elements are easy to find as neutral atoms. Elements like inert argon gas in our atmosphere or metallic gold in the ground. They're rare indeed, but when one of those elements is found, it's almost always found as a neutral atom. But not all elements are so well behaved. Potassium, for example, is never found as isolated neutral potassium atoms. Wherever we find sodium, be it dissolved in oceans or complexed in minerals, it seems to always appear as a positively charged cation with a charge of +1. So, why the difference? Why do some elements seem to enjoy simply being themselves, while others tend to appear as ions of very specific charges when we do find them? Well, think back to our lectures on the structures of atoms, when we saw how neutral atoms can be excited from their so-called ground states using light or electricity. When the proper amount of energy was added, the electrons could be promoted into higher energy levels within the atom, creating an excited state in which the atom still owns that electron, but the electron occupies an orbital farther out than usual. We acknowledge that different atoms require different amounts of energy to promote those electrons, a property which gives each one a unique line emission spectrum, allowing us to make that beautiful rainbow of colors using just a few different elements in combination with one another in neon lamps. Now, imagine what would happen if we imparted so much energy to a neutral atom that its outermost electron wasn't promoted to a higher energy level, but instead completely ejected from the atom, essentially promoting it to the infinity level, if such a thing exists. Now, when this happens, the loss of a negatively charged electron means that a cation has been formed, a positively charged version of the atom which has drastically different properties than the atom itself. The amount of energy needed to remove an electron from an atom and create a cation with a +1 charge is known as a first ionization energy. And as you might guess, the ionization energy of elements trends periodically. In order to remove an electron from an atom, we have to overcome the attractive forces that hold that electron in its orbit. And recall that electrostatic attraction is a function of overall charge and distance between two oppositely charged species. Let's take a look. Let's consider the ionization energy of different elements as we move up and down columns and left to right across rows. Specifically, let's take a look at the ionization energies of these elements: the alkali metals lithium, sodium, potassium, and rubidium. Now, these elements have electron configurations that look like this. Lithium is a 1s2, 2s1. Sodium is a 3s1. Potassium a 4s1. And rubidium a 5s1. And remember, we're moving up and down within a column here. So for this particular set of properties, we're going to be considering, again, valence shells. That's really the driving force in the chemistry of these elements. Now, let's think about what happens as we move down that column and increase the size overall of the electron cloud. So here we have a 2s, 3s, 4s, and 5s. What that means is that the electron clouds look something like this. Look at the gigantic size of the electron cloud that is blocking this electron from this nucleus. It's screening the attractive forces. In other words, this very, very positively charged rubidium nucleus is having trouble seeing this electron because it has to look through an ocean of negative charge to get there. So that electron is held fairly loosely. In contrast, if we come over here and look at sodium or even lithium, you'll notice that there is a far, far smaller sea of electrons blocking the outermost electron from that nucleus that is attracting it with its positive charge. Now, the consequence of this is that it's easier to knock an electron out of a larger atom. So, when we look at the energies required to liberate that outermost electron from lithium, it takes actually quite a bit to get in there and eject it and get it free of the influence of its nucleus. Sodium being a bit larger, its outermost electron is screened somewhat. It takes a bit less energy. And potassium even less, and rubidium, very, very little energy. It ionizes very easily. So this means that the trend of ionization energies as we move through a column is to have increasing ionization energy as we go upward or decreasing energy as we go downward. Now let's think about how rows are going to get involved here. Let's take a look at the third row of the periodic table, sodium through argon. Now, how might the structures of these atoms affect their ionization energies? Well, remember, we're moving across a row now, so your instinct is probably telling you nuclear charge, and you'd be right. Because remember, we're not changing the valence shell anymore. So the ocean of electrons that's screening those outermost electrons from the nucleus is the same size for all of them. So that can't be the cause here. Instead, the cause is that positive nuclear charge. Remember that as we move across a row to the right, we get a more dense nuclear charge pulling in harder on those electrons. So argon will hold it very tightly, as opposed to sodium at the other end of the spectrum here, in which it's only about half as much nuclear charge, so it's not holding them as tightly. As a consequence, if we look at how much energy it takes to liberate one of the outermost electrons from each of these elements, we see a profile that looks something like this, with a very distinct general trend of having an increasing ionization energy as we go from left to right. In other words, sodium can lose an electron more easily than magnesium, much more easily than, say, chlorine or argon ever could. Now, the reason for this is in part because of the nuclear charge, but also you'll notice a few little dips in the trend here. Most specifically, if we get over to aluminum, you'll notice that aluminum, when it's ionized, having lost one electron, has a 3s2 configuration. And having that partially filled valence shell, where only the s subshell is filled, gives a little bit of extra stability. So even if you do notice a few variations in the trend here, this trend generally holds because of the nuclear charge. So again, our overall trends in ionization energy as we move through the periodic table are to have increasing ionization energy as we move from left to right and from bottom to top. Now think back to the group 1 elements from our example. These elements are all from the same group, and so they react in similar ways. For example, each will react with water, ionizing the alkali metal, producing hydrogen gas and hydroxide ion in the process. But the trend in ionization energies of these elements creates a pronounced difference in just how vigorously this reaction happens. I'd like to show you this difference now, but these reactions can be very vigorous and can create some potentially unsafe conditions. So we're going to have to return to a safe place to make those observations. Okay, now that we're in a safe place where we can observe these reactions or these properties of alkali metals, I've secured 3 of them for us to look at. I have lithium metal, which is from the 2nd row of the periodic table. I have sodium metal, which is from the 3rd row, and potassium metal, which comes from the 4th row of the periodic table. Now, each one has just one valence electron that it's going to lose in a reaction with water to form hydrogen gas, which is flammable, what's called a hydroxide ion, which we're going to detect using a very special compound called an indicator. Essentially, it's going to turn red when these hydroxide ions form in solution. But of course, what we're really out to observe is the formation of the ions of these 3 that take place during the reaction. And even more specifically, just how vigorously these reactions take place. Because we've already predicted, based upon the periodic table's own structure, that we should see a trend in exactly how rapidly and violently these reactions take place. So let's get started with lithium. Now, before we begin, I'd like to show you that these really are metals. They don't look very metallic right now, but that's because they're oxidized on the outside, and they're also in a solution, or underneath of a liquid, I should say, of toluene, a solvent that protects them from the air. But let's take a look at sodium here, as it really would look as an element. I'm just going to grab a piece of sodium here. And what I'm going to do is just cut that piece of sodium in half so that we can see a freshly exposed surface, and you'll see that sodium is in fact a metal. So you can clearly see here from my freshly cut piece that this is indeed a metal, and you can also probably tell by the way I was able to cut it that alkali metals are actually quite soft. But in fact, they are metals. And you also probably noticed how easy they were to cut. And this is a property of all alkali metals. They're actually quite soft. But now that we've taken a look at sodium in its unoxidized pure state, let's go back to lithium and begin with what we expect to be the least reactive of the 3, and then see if the trend that we predicted actually holds when it comes to this particular reaction, which is driven by first ionization potentials. Okay, now we're ready to watch lithium react, because I've got my beaker full of water here, which also contains that special indicator, and I've got my lithium metal here. So let's grab a piece of lithium. And we're going to add this and keep a close eye on not only what's happening, but exactly how vigorously it's happening. And you can see the solution is beginning to turn reddish, an indication that we're making hydroxide. And there's also obviously a gas forming, and that's hydrogen gas that's effervescing. But also you'll notice by the end of the reaction that that lithium chunk will be gone, because it's no longer lithium metal. It's now lithium-1 ions dissolved into solution. Okay, my reaction is complete, and as you can see, the lithium metal is completely gone. It's been totally converted into lithium +1 ions, and it was a fairly vigorous reaction. But if our predictions about first ionization potential were correct, we should see a much more vigorous reaction when instead we use sodium. So let's try that now. Now remember, if our prediction's correct, sodium, which comes from row 3 of the periodic table, has an entire extra valence shell of electrons screening that outermost electron from the attractive force of the nucleus. In other words, it should ionize much more easily. So let's find out if it does. Again, exact same reaction is taking place here, except for turning sodium metal into sodium ions instead of lithium metal into lithium ions. Here we go. Now here you can see that the reaction is going more vigorously. In fact, so vigorously that the heat it generates has melted the sodium metal, and it's actually a little ball of sodium metal now that's dancing around on the surface of the water. Oh, there we go. And that little bit of hydrogen gas ignited right at the end. Evidence that we are, in fact, conducting the reaction that we believe we are. So that was a fairly vigorous reaction compared to lithium. But does the trend continue? Let's find out by running the same reaction using potassium metal. I've reset my water with indicator in it. Now it's time to see how potassium reacts.
Put this off to the side a bit here. Okay, here is potassium. All right. Now, regardless of what you may have thought of the sodium and lithium reactions, I think we can all agree that this reaction was far more violent. Right? Same exact reaction. The only difference was that our alkali metals came from different rows of the periodic table, a periodic trend.
The flip side of the first ionization potential coin is what's known as electronegativity. Just as first ionization potential measures how easily an electron is lost by a neutral atom, electronegativity refers to how easily an electron is picked up by a neutral atom. Not surprisingly, we see that the trend is essentially reversed from that of our first ionization potential, with elements like fluorine having the greatest electronegativity, while elements like cesium and francium have very, very small electronegativities. We report electronegativities of atoms in special units on a scale named for famed American chemist Linus Pauling. The Pauling scale ranges from 0 to 4, with 4 being the most electronegative element known, fluorine. At the far left and bottom of the table are cesium and francium, both of which have the lowest electronegativity of any known element, 0.8. The reasons for this trend are similar to those for ionization potential trends. Atoms want to acquire electrons to form octets. So, elements like fluorine, which are just one electron shy of an octet, are extremely hungry for an electron. That octet is just so close that they can taste it. On the other hand, you have elements at the left side of the table, which are so far from filling their valence shell with an octet that they can't possibly benefit from acquiring just one electron. Of course, the obvious exception to this trend, again, is the noble gases, which already have a full octet. Since they're already happy, they really have no strong tendency to gain or lose electrons. So let's sum up what we covered today. This was an exciting lecture because we took a look back at a topic that we previously covered, but we did so with new eyes. We investigated Mendeleev's periodic table of the elements through the lens of atomic structure that only became available a generation after Mendeleev's first breakthrough. We saw how Mendeleev's original method of listing elements by atomic mass was a happy accident, that in truth, the atomic number, the number of protons in the nucleus of an element, is used as a criterion for ordering. Mendeleev used chemical reactivity and physical appearance of elements to decide when to break his list and begin a new row. And we now know that the reason this works is because each time a new valence shell is started, new valence shell configurations fill predictably based on the Aufbau order, creating those patterns in the reactivity. Then we touched on a few properties of elements that trend as we move through the table in different ways. We talked about atomic and ionic radii. We saw how important the valence shell of an atom is in determining its radius, leading to ever larger atoms as we move downward through a column, and how the pull of more and more powerfully charged nuclei on the same valence shell leads to diminishing size as we move left to right within a row. We saw how the first ionization potential is reduced as elements in a group grow in size, as a result of the screening of the nucleus by interior electrons. We also saw how this trend dictates the ferocity with which each of these elements reacts with water as we move down that column. Then we discussed electronegativity, the alter ego to first ionization potential. More electronegative elements accepting electrons with greater ease. It's fitting that we ended on the topic of just how likely atoms are to release or accept electrons, because it's the exchange and sharing of electrons between and among atoms that bonds them together to form what are known as molecules. We're going to investigate that process in great detail next time.